A baseball is hit with a velocity of 28 meters per second at an angle of 30 degrees to the horizontal, at an initial height of 1 meter above the plate. This thing here is the plate. So this height here is 1 meter. Ignore air resistance in your calculations. How long does it take the ball to return to the initial height above the ground? All right, so first two things that should pop off in your mind is how long does it take? This is a time of flight question. Now, I've already done a video on the 3 most common quantitative question types that you'll get for the topic of projectile motion in HSC physics. If you'd like to watch that, click the link in the top right. And the second thing you should notice is return to the initial height. Right, so this question is saying that there's some projectile, it's being fired, it's going to follow this path. And it's not saying what's the time of flight to reach this position here. It's not saying like, okay, here's the initial position and here's the final position, find the time. That's not what it's saying. It's saying, here's the initial position, the final position you should consider as 1 meter above the ground, right? How long does it take to return to its initial height, right? So its initial height was 1 meter above the ground. So the final position that you're considering will also be 1 meter above the ground. So initial position is here and final position is here. So the first thing that I would do is find the horizontal and vertical components of the initial velocity, right? So I'd make a triangle like this with u equals 28 meters per second and the angle of 30 degrees. And then I'd find this uy and this ux. And we just do this using standard trigonometry. So let's try and find uy first. To find uy, you have to think about how is uy related to the information that we're given, the information being the 30 degrees and the 28 meters per second. Well, uy is opposite the 30 degree angle, and the 28 meters per second is the hypotenuse of this triangle. We have that little phrase, so katoa. And if we have something that is opposite and we have a value for a hypotenuse, opposite hypotenuse, we're using sine. All right, so we know that sine of a particular angle theta is equal to opposite over hypotenuse. In this case, the angle is 30 degrees. Angle is 30 degrees. The opposite is uy, and the hypotenuse is 28. So the hypotenuse has a value of 28. And so now we want uy, we want an expression for uy on its own. And so to get uy as the subject of this equation, we multiply this by 28 so that these 28s cancel out. And if we do something to one side of the equation, we have to do it to the other. So we multiply the other side by 28. Then we're left with 28 multiplied by sine 30. And sine of 30 degrees is an exact value. So if we go to our calculator and we put in sine of 30, we get 0.5, so a half, which means that this is 28 multiplied by a half, and half of 28 is just 14. So we found that uy is equal to 14 meters per second. We do a similar thing for ux. So ux is adjacent to the 30 degrees, and we still have this hypotenuse of 28 meters per second. And so we know that we use cos when we have an adjacent and a hypotenuse. So cos of 30 is equal to adjacent over hypotenuse, where the adjacent here is ux, and the hypotenuse is still 28 meters per second. We do the same thing that we did for uy, where we want ux as an expression by itself. We multiply this side by 28 to make this cancel out. And if we do something to one side, we have to do it to the other. And then we're left with 28 multiplied by cos of 30 degrees. Cos of 30 degrees is also an exact value. Here's a little trick if you don't remember your exact values. I never did. And so if we put cos 30 into the calculator, we're given some really disgusting number, right? We're given this disgusting number. And the whole point of exact values is to write this number without simplifying it, without compressing it. We want the exact value of it. But we can't just put it into the calculator because it gives us this ugly number. What happens if instead of just putting in cos 30, we put in cos 30 squared? So what's the square of this number? Ooh, it's a very nice number. 0.75, which in fractional form is 3/4. We take the square root of both sides, and then we're left with cos of 30 degrees on the left-hand side is equal to the square root of 3/4. And the square root of 3/4 can be written as the square root of 3 over the square root of 4. And the square root of 4 is just 2, which if you wanted to, you could find that out in your calculator as well. So we know that cos 30 degrees is equal to root 3/2, and that's our exact value that we can substitute into our expression. So we have ux is equal to 28 multiplied by root 3/2. The 2 divides this 28 and leaves us with a 14 multiplied by root 3. So the value of ux is 14 root 3 meters per second. And so once we've got the x and y components of the initial velocity, we would draw up a SUVAT table. So SUVAT is an acronym for displacement, initial velocity, final velocity, and acceleration, and time. And then if I take this, I'm going to make a copy of it. And what we do with a SUVAT table is consider all these values for the x component and also all these values for the y component. And we just put in anything that we know into this table so it can be staring at us in the face. So do we know anything about the x displacement of this projectile's motion? Do we know anything about this displacement here? No, we don't. We don't have a value for that. Do we know anything about ux? Yes, we do, because we just found it. It's 14 root 3. So ux is 14 root 3 meters per second. I'll make that blue. Do we know anything about the final velocity? Well, we can figure it out very easily because we know that the acceleration in the horizontal component of the projectile's motion is 0 because there's no force on the horizontal component of the projectile's motion. So acceleration in the x component is 0 meters per second squared. If there's no acceleration, that means the initial velocity is the same as the final velocity. So the final velocity is 14 root 3 meters per second. T is the thing that we're trying to find. And because it's not actually specifically related to the x or y, we can kind of write it in the middle as its own thing, right? Because it's the thing that we're trying to find, I like to notate that with a question mark. So this is the thing we're trying to find. SY, do we know anything about SY? Yes, we do. What's the displacement in the y component of the final position relative to the initial position? Well, the initial position is 1 meter above the ground, and the final position is also 1 meter above the ground. So the displacement in the y component, the displacement in the vertical component is 0. So there's no displacement in the vertical component. So we know that SY is 0 meters. If we were considering the final position to be up here, say, for the maximum height, then we would have a positive SY. We'd have some positive value for SY. If we were considering the final position to be down here, when it hits the floor, we would have a negative SY. So we'd have SY equals negative 1 meter, right? But because we're considering the final position as in line with the initial position in terms of its height above the ground, there is no displacement in the y component. UY, do we have a value for UY? Yes, we do. It's 14 meters per second. So UY is 14 meters per second. And we just found that with trigonometry. VY, do we know anything about VY? No, we don't. Do we know anything about AY? Yes, we do. We're on Earth, presumably. So this is 9.8 or negative 9.8 meters per second squared. So using all of this information, we now need to find t, which is the time that it takes from the projectile to move from this position to this position. So the next step is to recall our kinematic equations. So that's v squared equals u squared plus 2as, v equals u plus at, and s equals ut plus half at squared. And we're trying to find time, right? We're trying to find a value for time. And the second equation has a variable with time in it. The third equation has variables with time in it. The first equation does not have a time variable, so we're going to ignore that for now. So these are the two possible equations that we use. if we, okay, now we have a choice between using the data for the X component of the projectile's motion and data for the Y component of the projectile's motion. So we need to figure out, okay, which set of data are we going to use? What happens if we substitute the X values into these equations? Well, if we look at this equation here, if we substitute Vx in, we get 14 root 3 is equal to 14 root 3, right? That's V equals U. And then plus AT is going to be plus 0, because there's no acceleration in the X component, multiplied by T. Now T is the thing we're trying to find, and that 0 has just wiped out the T and has told us that 14 root 3 is equal to 14 root 3. So that's not useful. So we can't use the X data for in this equation. So what about the other equation? Can we use the data for can we use the X data for the other equation? Well, no, because we don't have an S. The other equation has an S and we do not have an SX. So what we're left with is the Y component data. So we're going to ignore the X component data. Perhaps we can use the Y component data. Now, like I said, both these equations have a T, which is good because the T is the thing that we're looking for. So both these equations have a T. We have a U, and both these equations have a U. We have an A, both these equations have an A. Do we have a V? No, we don't have a V. And this equation has a V. So we can't use that equation. This last equation, the only unticked variable so far is the S, and we do have an S. We do have a displacement. So we can use this equation with the Y component data. So that's exactly what I'm going to do. So if I just make this a little bit bigger, and I'm going to label each of the relevant variables with the subscript Y, just to remind myself that I'm working in the Y component of the projectile's motion. All right, so substituting in these values, Sy is 0, equal to Uy, which is 14 multiplied by T, plus half of Ay, which is negative 9.8, multiplied by T squared. We can write this a little more simply as 0 equals 14 multiplied by T minus 4.9 T squared. That minus 4.9 is just half of negative 9.8. So what we can do to the right-hand side of the equation is factorize out a T, so that we're left with T multiplied in brackets 14 minus 4.9 T. And this is all equal to 0. I'm going to write the 0 on the other side just because it looks neater. So when we have an equation in the form A multiplied by B equals 0, we know that for this equation to be true, A can be 0 or B can be 0, right? So we know from this equation that either T equals 0 and slash or 14 minus 4.9 T equals 0. Now this T0 is just, that's referring to the start of the projectile's motion, right? Why might the equation be spitting out information about the start of the projectile's motion? Well, the information that we put into the equation is that the displacement in the Y component is 0. Now, there are 2 points on the projectile's path where the displacement in the Y component is 0. The one that we're interested in is the one at the final position here, right? This is the one, this is the whole point of the question, is finding the time that it takes to get here. But there's another point on the projectile's motion where the displacement in the Y component is 0, and that's at the very start. That's the initial position. So we put in data saying that the displacement in the Y component is 0, and there are 2 points at which that is true, and that is why we are getting 2 values for time from this. That's why it's spitting out 2 values for time, right? So T equals 0, that's referring to the start, which we are not interested in. We can rewrite this as 14 equals 4.9T by plussing 4.9T to both sides. We can switch the equation around so we have 4.9T is equal to 14. We can then divide both sides by 4.9 such that these two 4.9s cancel each other out, and we're left with T equals 14 over 4.9. And if you put that into a calculator, 14 divided by 4.9, we are left with 2.86 if we write it to 2 decimal places, right? So T equals 2.86 seconds when written to 2 decimal places. And that's the answer to the question. That's the time that it takes the projectile to go from its initial position here to a final position in which its displacement in the Y component is 0, in which it, like, it goes from its initial position to a point where it returns to its initial height, right? And that's the time it takes. T equals 2.86 seconds. All right. Part B, the ball is hit directly towards a stationary outfielder who is 85 meters away from the plate. Okay, so this is the stationary outfielder. This is her initial position. And initially she's 85 meters horizontally away from this plate here. This like diamond plate thing here. At the instant the ball is hit, the outfielder begins to run towards the plate with a constant acceleration. All right, so at the instant the ball is hit, this person starts running with a constant acceleration. Some constant acceleration. I'm going to draw it in red. Everything, all the information that is in red is going to be associated with the outfielder, and all the information written in blue I'm going to associate with the projectile. All right, so at the instant the ball is hit, the outfielder begins to run towards the plate with constant acceleration. What is the magnitude of her acceleration if she catches the ball when it is 0.50 meters above the ground? All right, so what this is saying is the outfielder is initially here. She starts running towards the ball once it's launched. And when the ball reaches this position here, which is 0.5 meters above the ground, 0.50 meters above the ground, this distance here, she catches it at that position. So given all this information, what is the acceleration? What is the constant acceleration of the outfielder? So another thing that we're told is that initially the outfielder is stationary, right? The ball is hit directly towards a stationary outfielder. So that tells us that this person here has an initial velocity in the x component of 0 meters per second. But that's pretty much all we know, right? We know that the ball starts 1 meter above the ground. We know that it ends, so let me just draw this here. Its initial position is 1 meter above the ground. Its final position is 0.50 meters above the ground, so 0.5 meters above the ground, half a meter. And we know that at that position, the outfielder catches it. This is quite a tricky question. There's a lot of stuff going on. You're not just considering the motion of the projectile, you also have to consider the motion of this person. So one thing that we do know is that the initial velocity of the projectile is the same as the previous question. So if we do a SUVAT table, we already know two pieces of information that we'd normally have to work to find. So we already know, what the initial velocity in the y component is and the initial velocity in the x component is, because we did it in the previous question, right? So ux was 14 root 3. Ux was 14 root 3 meters per second. And uy was 14 meters per second, or is 14 meters per second. We also know that the acceleration due to gravity is negative 9.8 meters per second squared. We also know that there's no acceleration in the horizontal component. And from that, we can deduce that the final velocity in the x component is equal to the initial velocity. Do we know anything about the displacement in the x component? Do we know anything about this distance here? No, we don't, so we leave it blank. Do we know anything about sy? Now, in the previous question, we were considering this as the initial position of the projectile and this as the final position of the projectile. And they were in line with each other in the y component, right? And our sy was 0. That's not the case here. Right now, the final position we're considering has the projectile half a meter above the ground. So you might be tempted to write 0.50 meters. That's not exactly correct, because although it is 0.5 meters above the ground isn't the reference point that we're considering for displacement, right? If the ground was the reference point and you wrote 0.5, then you'd be correct, but that the ground isn't the reference point. The reference point is the initial position of the projectile. So from this reference point, from this height, what is the displacement of the projectile at the final position? Well, it's not 0.5, it's negative 0.5, negative 0.5, because this whole height here is 1 meter, and the ball is half a meter above the ground, and so that leaves half a meter from the initial height, right? So the displacement in the y component is negative 0.50. Do we know anything about Vy? No, we don't. Okay, so all this information in blue is data related to the projectile. So this is projectile data. Now in red, I'll do the same thing except for the outfielder instead of the projectile. So the reason I'm only copying S of X is because the outfielder has no motion in the vertical component, right? We don't have to concern ourselves with the Y component because there is no motion in the Y component for the outfielder. All right, so do we know the X displacement of the outfielder? Meaning, do we know the distance from the final position to the initial position? Do we know this distance here? No, we don't. That's definitely something that we need to find out if we want to find the acceleration though. And that's something I should probably do, is say that the acceleration here, this value here, that's what we're trying to find. That's the entire point of the question. Do we know something about ux? Yes, we do. We do know something about ux. We know that it's a 0 because we're told in the question that initially it's a stationary outfielder, and stationary means velocity of 0 meters per second. So we know that ux for the outfielder, so this is outfielder data. This is outfielder data. We know that ux is 0 meters per second. Do we know what vx is? No, we don't. Oh, okay, so what the hell do we do with all of this information? Well, one thing that I haven't written yet is time. And time is the variable that really relates these two pieces of data together with each other, right? And why is that? Well, the time that the person starts running is the same as the time at which the projectile is launched. And similarly, the time that the outfielder reaches this position here is the same time which the projectile reaches this position here. So time is kind of like the glue that's connecting these two pieces of data. Time is the thing that these two sets of data have in common. So we can use the data from the projectile here to find a value for time, and then we can use time in our calculations of things over here, right? So how do we find the time? Well, now we have more data relating to the projectile than we do relating to the outfielder. And so I'm going to focus on the projectile data here. So if we again recall our kinematic equations, v squared equals u squared plus 2as, v equals u plus at, and s equals ut plus half at squared. And we look at the data in the x component, remembering that we're looking for a time. Like we're in the same position that we were in part A of this question, where if we sub in the data for the x component when we're trying to find a time, it's just going to be useless, right? Because first of all, this first equation, because we're trying to find a t, that's useless because it doesn't have a t. If we're using the x data, we don't have an s, so the third equation becomes useless. And because the acceleration in the x component is 0, it turns this second equation into being useless because it'll just make this disappear. It's the same problem that we had with the last question. So again, we're just going to ignore this x data. Now we're trying to find a t, and we have s, u, and a for the y component. S, u, a, and we're trying to find a t. This has u, a, and t. It has a v, which we don't have when considering the y component data. So we're going to remove that equation and again work with this s equals ut plus half at squared equation. And again, we're going to label each relevant variable with the subscript y to remind ourselves that we're working in the y component. Now we sub in each of these values, right? So Sy is negative 0.5. You can write 0.50 if you want, but it's just easier to write 0.5. Uy is 14 meters per second multiplied by t plus half of negative 9.8, which is the ay here, multiplied by t squared. Now we can write this a little more simply as negative 0.5 is equal to 14t minus 4.9 t squared. Again, negative 4.9 is just half of negative 9.8. And then I'm going to reshuffle this equation around a little bit just so it looks a bit neater. So I'm going to take this 4.9 t squared to the other side. That's just plussing 4.9 t squared to both sides of the equation. I'm going to take the 14t to the other side so that it's negative 14t. That's just minusing 14t from both sides of the equation. And then we're just left with this negative 0.5 equals 0. Now in the previous question, we had something that looks similar to this. And what did we do? Well, we factorized a t out. The reason we could factorize a t out is because we didn't have some extraneous number here. We didn't have a constant term on the end that was preventing us from factorizing. This time we do have a constant term, the negative 0.5. So we can't actually factorize out a t. This, though, is in the form of ax squared plus bx plus c equals 0, which is a quadratic equation. Instead of an x, though, we have the variable t, which doesn't really change anything because it's still just some variable, right? It's still just representing a variable. So in this case, our a is 4.9, our b is negative 14, and our c is negative 0.5. And the quadratic equation is t, because that's our variable. Usually you'd write x, but because we're using t, we write t. T equals minus b plus or minus the square root of b squared minus 4ac divided by 2 times a. Now if we sub our values for a, b, and c into this equation, we get b is negative 14. Whoops, b is negative 14 plus or minus b squared, which again is negative 14, minus 4 times a, which is 4.9, times c, which is negative 0.5, divided by 2a, which is 2 times 4.9. We can write this a little more simply as 14, because negative times a negative is a positive, so 14 plus or minus the square root of this ugly thing here, which I'll come back to in a second, all divided by 2 times 4.9, which is 9.8. I'm going to put this expression that's under the square root term in my calculator, and if you don't believe the value that I give you, you can do it yourself if you want. And I mean, you should probably try these questions yourself before watching me do it, because then you could, at the very least, see where your misconceptions are if you're not able to do it fully. But putting this into the calculator, you get a value of 205.8. 205.8. So this is a little weird. Again, we have two values for t, right? In the first part, in part A, we had two values for t, but one of those values were, where is it? Here it is. Okay. In the first part, we had two values for t, but one of those values was 0, which makes sense because it's, okay, t equals 0 is something that exists on the projectile's path, right? We know what that means physically. But what does it mean physically if we have a negative time value, right? So the two t values that we have here is 14 minus the root of 205.8 divided by 9.8. That's one value for t that we have. And the other one is t equals 14 plus root of 205.8 divided by 9.8. Now we can see right away that this one is definitely positive because we've got a positive number added to another positive number. So we know it's going to be positive. This one we have a positive number minus a number. So we don't know whether this is positive or negative yet, but if you put this in the calculator, you get 14 minus root 205.8 divided by 9.8. You get negative 0.03527 blah, 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 blah. You get a negative number. So I just want to reiterate, when we got a t equals 0, it wasn't the time that we were concerned with, but it's pretty obvious what it means physically. It's at the start of the projectile's motion. Negative time, what the hell does that mean? Well, I'll tell you what it means. These equations are quite blind to the actual question that you're doing, right? They don't know exactly where the projectile starts and exactly where the projectile ends. The equations are blind. And what they're seeing, what the math equations are seeing, is that they're just seeing a description of a parabola that goes on forever, right? They're seeing, as you would in math, right? The equations are just seeing a parabola that goes on forever. So remember, we put into this equation the information that the displacement in the y component is negative 0.5 meters. And there are 2 points on this theoretical parabola where the displacement in the y component is negative 0.5 meters. The first place is the thing that we're concerned about, right? The final position of our projectile. The other place doesn't actually exist in physical reality, right? It only exists on this imaginary parabola that the equations are seeing, the blind equations are seeing, right? The other point where the displacement in the y component is also negative 0.5 is this place here. That doesn't exist. What the equation is telling us is that if you start at this initial position and you go back in time, what was it, like, negative 0.3 something seconds, you will reach a position on this imaginary parabola where you are negative 0.5 displaced in the y component from the initial position. That's what it's telling us. And I wanted to tell you that just so you have a more comprehensive understanding of the math behind this. But it's not actually useful in this particular question, right? So again, we're ignoring that piece of data, even though I think it's a really cool piece of data. All right, so the time that we're concerned about is this one here. And if you put that into the calculator, you're left with 2.89242, and that's to 5 decimal places, which will probably be accurate enough. Why not? Well, actually, you know what? We'll put one more. 6 decimal places. Okay, so now we have this value for time here to 6 decimal places. So this time thing here is this. And I'm just going to remove all this working. And now what can we do? Okay, we have a value for the time that it takes for the projectile to go from the initial position that we're considering to the final position that we're considering, where the initial position is here and the final position is, and the final position is the point where it's caught by the outfielder. So we know that time. Now we can use that time to find out some information about this distance here, right? Just looking forward in the question a little bit, in order to find the acceleration, we're going to have to find something about the change in velocity, right? Because that's the like fundamental definition of acceleration, is that acceleration is change in velocity over the change in time that was required for that change in velocity to occur. And in order to find out about velocity, we have to find out about displacement. We know this distance here is 85 meters. And we are trying to find this distance here. If we know the green distance and we're trying to find the pink distance, then if we find this blue distance, we can just minus the blue distance from the green distance to find the pink distance, right? And that's exactly what we're going to do. So first we need to find this SX here. So I'm going to uncross out the cross over the X component data, and I'm going to try and find this SX here. Now that we have T, it is something that we can do. So again, I'm going to use that equation. Actually, I'll just quickly do this again. Kinematic equations: v squared equals u squared plus 2as, v equals u plus at, s equals ut plus half at squared. So now we're trying to find an s. We're trying to find a displacement. So we need to use an equation that has an s in it. So the first equation has an s in it, and the third equation has an s in it. So this second equation we can't use. we have a u, so both of these have a u. We have a v, the first one has a v, the second one doesn't. And we have an a, both of them have an a. All right, so this equation here has all the things ticked. Why don't we use that? Again, we'd run into this same annoying problem where if we substitute ax equals 0, it gets rid of all the useful stuff, and we're just left with a v squared equals a u squared. So we're not going to be using that equation. We're going to be using this equation. Again, this tends to be a very useful, a particularly useful equation. All right, so this time we're considering the x component of the motion. And if we substitute in the values that we have an sx, which is the thing we are trying to find. So maybe I'll make that a little distinct. Sx is the thing we are trying to find. Ux we have as 14 root 3. So Ux we have as 14 root 3. And t we now know to be this thing here, 2.892421, plus half of ax, which is 0, because there's no acceleration in the x component, multiplied by t squared. The 0 destroys all of this stuff here, and we're just left with 14 root 3 multiplied by this number. And so I'm not actually going to evaluate it. I'm just going to leave it like that, just to have it as a more precise value, because it's not our final answer, is it? It's just something that we're using as a stepping stone to the final answer. So there's not really any reason other than convenience to simplify it, but simplifying it might actually make it, there's not a whole lot of difference in convenience between this expression here and an expression that's just kind of a string of numbers, right? So I'm not going to bother evaluating it. The time that it takes is not worth it, in my opinion. You can evaluate it if you want, I don't care. I'm going to delete this because I don't need it anymore. So now we know this sx here. Now, what was the whole point of finding that sx? The entire point of finding that sx was in order to find this sx, right? Where the blue sx has to do with the projectile and the red sx has to do with the outfielder. So this red sx is equal to 85, which is the green distance, the distance highlighted in green, minus the blue sx, which is the range of the projectile. So 85 minus this monstrosity here, 14 root 3 multiplied by that other number. And I will evaluate this because it would be nice. Again, putting that in the calculator is 85 minus 14 multiplied by root 3 multiplied by 2.892421, which leaves us with an SX of 14.862518. That's to 6 decimal places. Again, the reason I'm writing 6 decimal places instead of something more compact like 2 is because it's not our final answer, right? It's, again, just a stepping stone. But 6 decimal places will probably be adequate in terms of accuracy. So we know this distance here, this SX here. Okay, so we have the distance that was used here for the outfielder to run from her initial position to her final position. We also have a value for the time that it took for her to run that distance, right? It's the same as the time that it took for the projectile to move from its initial position to its final position. And so we can, again, use kinematic equations to solve for AX, I think. To solve for AX, I think we might have to solve for VX first and then AX, or it might just be AX. Let's see. I'm on the ride with you here. Okay, V squared equals U squared plus 2AS. V equals U plus AT. By the way, the reason I'm writing these out each time is to, like, get you to remember them a little bit. So, anyway, S equals UT plus half AT squared. So, what are we looking for? We're looking for an A. All of them have an A. A. We have a T. These two have a T. We have an S. This one has an S and this one has an S. We have a U. This one has a U, this one has a U, this one has a U. And this has a T here, which we already ticked. And we don't have a final velocity. I'll look at that. Again, we're using the third equation. Very useful this equation is. All right, so we can use the third equation to just solve for AX. And maybe I'll write it down here where there's more space. Okay, so now we're considering the outfielder, and this is in the X component. So SX is this number here, which I'm not going to rewrite. I'm just going to copy. SX is this number here. And UX, the initial velocity in the X direction, UX, what was that again? That was 0 because she started stationary. So that's a 0. The time was 2.892421 plus half of the acceleration in the X component, which is the thing we are trying to find. So AX, the thing we are trying to find, multiplied by T squared, which is this number squared. This number squared. Okay, so now we just have to rearrange this whole thing for AX. So on the left-hand side, we have 14.862518 equals, the 0 wipes all this out, so we don't need to bother with it, is equal to half of this thing squared multiplied by AX. And I just changed the order of these things here because it looks a little neater. So if we multiply both sides by 2, we can get rid of this half fraction here. So multiply this side by 2. And then if we divide both sides by this expression here, if we divide by 2.892421 squared, and I'm just going to copy it because, geez, that's a long number. If we divide both sides by this number here, then the number will cancel out with itself, and we'll be left with AX equals this thing here. AX equals this thing here. We're almost to our answer. So if we put this into the calculator, we get 2 multiplied by 14.862518 divided by 2.892421 squared, which leaves us with 3.56 meters per second squared because it's an acceleration, and that's written to 2 decimal places. Right, so this is our final answer for the acceleration.